Ladies and gentlemen, I present to you the final example from section 8.2, all about finding the volumes of certain three-dimensional figures. Figures that are created through rotations. Part 4. You never thought it would go on this long, did you? Let's read the problem, shall we? This is on page 381. 381, section 8.2. Here is the problem. The region bounded by the line x plus 2 and the parabola x squared is rotated about the x-axis. Find the volume of the solid generated. Okay, so they don't tell us that it's first quadrant. They don't tell us anything else. They just tell us that there's a region bounded by these two graphs. Well, conveniently enough, I have the graphs, the pictures. I know what these graphs look like. They look like these guys. You could probably guess which graph is which. This guy is f of x equals x plus 2, and this guy here is g of x equals x squared, and the region bounded by the two is this. We're going to take this shape and we are going to rotate it around the x-axis, being right here. We're going to end up with a nifty three-dimensional shape, and we are going to use the washer method to find the volume of that shape. Now, before I show you what that shape looks like, let's, before I rotate this guy, which is the region bounded by the two graphs, there you go, you can see the similarities there. It's just the rest of the graph has been chopped off, because this is the only part of the graph that we really care about. Let's look at the parts independently. Here is the linear part of the graph. First of all, we need to know how much of this graph is going to be rotated. I'm going to be, in other words, what do I integrate from? From what to what? I probably should have done that right away. So I know this is going to be an integration problem. But I'm going to be integrating from this x value, x equals question mark, to this x value. Well, this is just the, these are just the intersection points of the two graphs. And this is what makes a problem like this maybe slightly more difficult than any of the other problems that we've done yet, because we don't know right off the bat from what to what we will be integrating. So we need to find those points through algebra. The way we do that, the way we find intersection points of any graphs, is we set the two formulas equal to one another and then use algebra to solve for x. This one works out real nicely. It turns into a factorable quadratic, and I end up with values for x of x equals 2 and x equals -1. This is -1. And this guy down here, that is x equals 2. So I'm going to be integrating something, an accumulation of something, from -1 to +2. Alright, so you don't need to see any of this anymore. Let's just get rid of that. And let's go back to looking at what shape we're going to get if we try to rotate this thing around the x-axis. So, boom. That's the thing I'm rotating. But I'm actually going to look at these in parts first. So let's look at the outside shape. You could probably guess what this is going to look like. We rotate this around the x-axis. We get this cone-looking thing. It's like a truncated cone. Looks like the end of it looks like a lampshade turned on its side. So that's the outside of this shape. The inside, though, is going to be a little strange looking. This is going to be the hollow part of the inside of the graph. And if we rotate this thing, let's revolve, we kind of get this strange looking thing. It's very skinny in the middle here, because at that point right in the middle along the x-axis, it actually touches the x-axis, so it actually has no width right here. It goes infinitely skinny. But what we're going to be doing is taking this volume and subtracting this volume from inside. So this is done by subtraction, taking this and subtracting this. So let's take a look at what that might look like. We're going to take this graph, let's revolve it nice and slow. There you can kind of see that shape coming around the x-axis. There it is, it's coming around, and we get this nice interesting graph here. It's sort of like a lampshade, but it's a little more sophisticated. So let's try to find the volume of this beautiful shape here. Here is a picture of that beautiful shape right there. Yeah, I don't think we need this picture anymore. We know what we're doing. We're integrating something from -1 to 2. And what we need to talk about are the cross sections. So the cross sections, just like all the other problems, the cross sections of this shape are circles. There's the end circles, the largest circle and the small circle, and let's just pick some random circle from the middle. Well, these circles are actually all going to be washers. If we go up to the graph here, we might be able to visualize a little better what one of these washers might actually look like. So let's, in black, let's pick some random value of x. Let's pick this guy right here. At x, we are going to have a circle. 1, 2, 3 from the top, so 1, 2, 3 from the bottom. And the inside of this is going to be hollowed out, just about like that. And it makes a washer. So that washer, like any washer, is going to be defined by pi r squared minus pi r squared, where the we'll call it pi big R squared minus pi little r squared, where big R represents the radius of the large circle from here to here. Call that big R. And I'm in green, from here to here, we'll call that little r. And the area of the entire washer is pi r squared minus pi r squared, or pi r squared minus r squared if you factor out the pi. So the radii are determined by the graphs. You got to figure out which graph is on top and which graph is below. The graph on top is going to determine big R. In this instance, big R is the distance from the x-axis all the way to the top here. That is to the graph x equals 2. So big R is going to equal x plus 2. Little r is going to be the lower of the two functions. That is actually my parabola. So little r is equal to just x squared. So the area of the entire washer is, no matter what x value I choose, the washer can be defined by pi times x plus 2 squared minus x squared squared. We can clean this up a little bit. Pi times x squared plus 4x plus 4 minus x to the 4th. It doesn't clean up all that nicely, really, but we can go back now to our other picture and put this into an integration problem. Might as well put the insides of these circles just to remind ourselves that these cross sections are actually going to be washers, something like that. And the area of each washer is x squared plus 4x plus, what is it, 4? 1? 4. Minus x to the 4th power dx. This is all going to be multiplied by pi. So I'm just going to bring the pi out immediately. The antiderivative. Lots of pieces to this one, so there's going to be lots of plugging in. 4x squared over 2, that's going to cancel out a little bit. And then minus x to the 5th over 5. It's kind of a pain because we have so many different denominators. It's not going to be a very pretty answer. Oh, especially if it disappears like that. And we're going to do this from -1 to 2. Let's just see what the book has to say about this. The book also does not bother with showing you all the steps after this point. It jumps straight to the end and tells you that you end up with 72/5 pi cubic units. 72/5 pi units cubed. So that's it. That's about as complicated a problem as you might see in this section 8.2. That's all for now. Stay tuned for 8.3. Goodbye.